Moving on to the day 5, session 3. Today, the session will be handled by Dr. Ajit from MA College, Kodamangalam. So let me invite Mr. Arun KR for introducing the speaker. Arun.
Good afternoon to all of you. Respected head of the department, Dr. Shanmugesh K, and our spokesperson, Dr. Ajit Joy. My name is Arun KR, Assistant Professor, Department of Mechanical Engineering, Vijay City. Now I am going to introduce our today's spokesperson, Dr. Ajit Joy. He is a professor of Department of Electronics Engineering, Marathaneshi's College of Engineering, Kodamangalam, and he completed his Bachelor of Engineering in 1996 from Mangalore University in Electronics and Communication Engineering, and also completed his post-graduation from Anna University in 2008. And also he completed his PhD from Anna University in 2017. And he has also more than 22 years experience in teaching and 2-year experience in industry. And he published a number of conference and journal papers, and secured a number of best outgoing students from PhD College of Technology, Coimbatore, and got a number of best paper award, especially 2018 CatCon and 2018 KSCST paper award. And he get a number of projects in 100 projects, now more than 900 projects. And his main area of specialization is embedded system, computer network, and robotics and automations. So with your all permission, I hand over the session to Dr. Ajit for taking the session. Thank you. Sir, I welcome.
Yeah, sure. Yeah, thank you, Dr. Shanmugesh and Mr. Arun. And good afternoon to all. I think this is the 5th day of the FDP. So you might have already acquainted with a lot of IoT technologies, a lot of inventions, advancements by this time. And I am basically from the field of electronics and communication. And my main interest is concentrated with embedded systems and application of embedded systems with computer networks, automation, and robotics. So I would like to concentrate much on the design tools of embedded systems, which is closely related to IoT. Okay. Shall we start the presentation?
Yes, sir.
I hope you can see these slides.
Yes, sir, it's visible. Sir.
Visible, okay. Wait 1 minute. From my side, yeah, okay. So we have a lot of advanced manufacturing systems now, especially in the era of Industry 4. We have actually the industrial systems as well as the manufacturing has been a lot of advancements. That is mainly because of the advancements in the sensors and actuators, the connectivity to the sensors and actuators, the availability of the sensors as separate modules, as well as a lot of actuators, motors, drives. So what has happened is whenever we interact any system with more number of sensors and actuators, the traceability, the predictability, as well as the effectiveness in the operation will get improved. So we are getting more close to the system. That is the main thing. And secondly, as a storage, a common storage or as a global storage, we have the cloud computing mechanism. So the big data, as well as the cyber security and the global access to the data for the database. So that will enlarge, that will widen the area with which we interact. And accessibility to the system or to the controls from anywhere also will get improved. And another advancement is in the 3D printing or the rapid prototyping. Not only the 3D printing or the rapid prototyping, different mechanism, additive and subtractive mechanisms can be used, as well as we can have digital copies of most of the systems. Okay, it includes everything. And the main advantage is, so in the normal case, we should have a lot of trials. So that may generate enough scrap also. That may be eliminated. As well as the customization also will become very easy. So once one system is developed, it can be reinvented or customized so that it can accommodate in another situation. And similarly, again, with by using the 3D printing or other additive and subtractive mechanisms, the fast prototyping is also possible. And next one is everything is made automated. Okay, by the help of different types of robotics, artificial intelligence, everything has been made automatic or automated. So the efficiency as well as the productivity of the entire system got improved. That is what is happening, what has happened in the industry recently. So these advancements are there, but to make it effective, so all should be connected. Okay, everything should be connected. So there, the role of Internet of Things come into picture. And so a lot of advantages we can see with the IoT technology in industry or manufacturing. Firstly, we can start with the quality control. And quality control means every point of manufacturing can be checked or verified by the usage of various sensors, or it can be sensors like it may be various types of parameters may be monitored, or directly the video may be taken and it may be monitored, and every equipment can be tested for functionality and for the deviation from the calibration. Okay, so all can be real-time monitored. That is the advantage. So the quality control is very easy with the IoT based systems. Then remote production control. So normally a factory environment, people are going to control a lot of machines and a lot of manpower is required. And reallocating all the controls from the factory location to another location where everything can be controlled, and the IoT make it possible, because the centralized computational resources can be stored into a cloud or some server, and it can be accessed from a common platform. So the remote production control is very much possible. And the next one is asset tracking. All the inventories which is required for the manufacturing can be very closely monitored. So wherever the stock is available, wherever by moving, wherever that inventory is available, so how much time it will take to reach the factory floor. So everything can be monitored. So that is the asset tracking. That is also part of, that is also made as part of the IoT technology. Then the logistics management. So they optimize the fuel cost and they can make smart deliveries. And so a lot of things can be diagnosed and repairs can be made very easily by logistics management. Then digital twins. So it is the digital copies or the miniature physical models. It could be 3D printed or it may be fabricated by using some other technology. So the use of these digital copies, we can foresee the functionality of that particular prototype, and the lifespan can be expected. Suppose the machine, we have to check whether the machine will run for someone like cycles. Okay, it can be very well tested with that miniature model, and the unforeseen bottlenecks or errors also can be detected and it can be corrected. So that is the digital twins. Then another important thing is the safety of the workers on the factory floor. So the presence or absence of the worker can be very easily identified, and inside the machinery damage or the vehicle mishaps, so all can be very well identified, or it can be monitored by using sensors or videos, and even the worker can have a wearable IoT sensor monitoring system. Okay, something like a cloth or something like that. Okay, so the worker safety can be very well implemented and continuously it can be monitored by using IoT. Then smart metering. Okay, smart meters that can monitor the consumption of water, electric power, or anything can be monitored. So the real-time monitoring is always possible with the IoT, and lot more can be added to these advantages. So that is how the IoT can be used to make the manufacturing more efficient, uh, more efficient. And again, whenever we think about IoT, so how big is it? That is what. Okay. So normally, I think this is a pre-COVID statistics, and in 60 seconds, a lot of things are happening with the help of internet or with the help of IoT or with the common storage. Okay. So you can see a lot of things: Skype calls, number of Skype calls, number of emails sent, number of search queries with Google, number of applications, iPhone or Android applications downloaded. So a lot of things are there. A lot of you cannot imagine how many operations are being done with the help of IoT. Okay, so that is the potential of IoT. Whenever we can bring this potential to the manufacturing, that is going to always it's going to help the efficiency of the manufacturing. And a lot of other advancements also were there to incorporate IoT in the manufacturing. Like here we see some domestic gadgets, not a commercial gadget or industrial gadget. See, all these gadgets, a small plug where automatically it will send the power consumption information, the voltage, the current consumed, as well as the wattage, the power consumed will be sent to the mobile attached to it. And it can be very well attached to the socket, power socket. And another, a small uh, on system computer, okay, or a system on chip type computer. Okay, so that can monitor a lot of parameters, and it very well it will send all these parameters to the server or to a cloud. And again, within the shoes, another sensor is inserted, and that sensor can monitor the number of steps you have already completed or the duration you have finished while jogging or walking. And similarly, a lot of wearable as well as a lot of devices which can be attached to our body or attached to the day-to-day appliances which we will work with. So a lot of devices are there. That is the household scenario. Then, so whenever we incorporate IoT in our real life, so other other sensors like the ECG sensor, a motion sensor, and or multiple motion sensors can be connected, and continuously it may be able to monitor the body parameters and can be sent to the internet or to the cloud. Okay, so it may be made available uh, to a physician or to a doctor. Okay, so that can be done. And another important thing is things are getting connected to things. So your vehicle is getting connected to a lot of other appliances, and a lot of things are going to monitor where is the nearest pump, where is the nearest restaurant, where is the nearest workshop. So automatically it will be identified. Okay, because everything is connected. Okay, so that kind of advantage are. So till now what we have discussed is everything is getting connected, like our body is getting connected to the cloud, the vehicle is getting connected to the cloud, and from an industrial floor everything is getting connected. So everything is basically it's all going to get connected. And so now why IoT is happening now? What is the reason? So there are a lot of improvements in the sensor technology. There are a lot of improvements in the miniature computers. We will see the number of sensors recently, the available sensor or sensor modules, miniature computers. So some 10 years back, so we would have heard about a very small computer like an Arduino board or a Raspberry board or a BeagleBone board or a Blue Pill board. Okay, but it's all available now. A miniature computers are very well available at a cheaper cost, and the availability is also very easy. So that is another reason. Low power wireless communication. So again, some years back there was no wireless communication which was this much cheap as nowadays, or which was a low power consuming device as what is available now, or a availability of the mobile devices or a cloud storage. It was not available. So now all these things are available. That is the reason IoT is emerging now. Then we will see some sensors which is directly connected accelerometer, you might have already heard about all the sensors. It's not new. It's not at all new. So Intel Joule, that's a development board. You can see the size of that Intel Joule development board. A Bluetooth LE, a low power Bluetooth module. Okay, a force sensor, a VG camera. So a lot of things are there. And another thing is the power is improved. Device power as well as or the computing power has been improved multi times. A MacBook Pro, it's a laptop, and you can see the basic specifications, a smartphone, which may be working with 1.5 or more than that speed, a wearable devices like a gear, like a watch, a Raspberry Pi board, Arduino board, Intel Joule board. So it's all available in the market, readily available in the market. That is the difference. Then availability of the wireless network. So whenever we depends on the wired network, it may not be easily made, it cannot be easily made available. The IoT connectivity cannot be made easily available because connectivity through wire is restricted always. We have a lot of wireless communications available, like wireless LAN, LTE, that is the mobile internet, 3G again mobile internet. Now it becomes 4G or even we are leaping to 5G. A Bluetooth, normal Bluetooth, a low power Bluetooth, Zigbee. You can see the speed also. Okay, so the speed is getting improved, the range is getting improved, the power is getting low, and the availability as well as the usage is also getting improved. Okay, so there is advantage. For example, the Bluetooth low power, you can see the power consumption. So it is 0.01 to 0.5 watt only. You can compare against the power consumption initially the wireless device were taking. It was something like in terms of watts or tens of watts. Now it has been changed. That is one of the main reasons. Then putting all together, we have an IoT system that is consisting of sensors, mobile devices, computers, and cloud. Okay, we will talk to each other by using BLE or Wi-Fi as appropriate. So different connectivity, different types of connectivity may be used. Okay, and in 2020 nowadays, so we can see everything is getting connected. I'm not going to elaborate it. So some typical example I have given, that's all. Okay, from healthcare monitoring or the elders monitoring or sports and fitness, then information capture, control, environmental sensors, lot of things are there. Everything is connected. So that is a basic concept. And things, the basic Internet of Things components, we have things and connectivity from things to a common platform. Then the data is available as a universal data, and there is analysis of that particular data. So that is basically it works. And again, another important thing is the growth of the internet speed. 1984, it started with the 2 kbps of speed. With the 2 kbps of speed, it cannot send digital data. So it was basically the transmission was using analog signals. So at the end points, it will be converted to the digital signal. Then the digital data was required. That was the basic idea at that time. And only intra-country network was possible at that time. There was no international roaming. And 1999, whenever 2G emerged, it is changed to the analog transmission changed to the digital transmission, and international roaming also was available. By 2002, again 3G came, speed is improved, the technology provide along with the digital signal provide the voice, data, and video along with the digital data. Okay, and 2010 again the speed is increased up to 200 to 1 Gbps. 4G came, the bandwidth got improved, and there was multimedia services and global roaming at a very lower cost. And by 2020 again we can see it's emerging to 5G, and there will maybe possibility of simultaneous access to different wireless network. Okay, so that is the growth. This growth helped IoT very much. And some of the commonly used small computers, there is a BeagleBone Black. You can see the size of that. Basically, it's a full computer. Basically, it's a full computer. Every interface is there. A BeagleBone Black, then Intel Galileo, then Arduino, Uno, and Raspberry Pi. And out of this, the Arduino as well as the Raspberry Pi is very common. Here, most of the students' project, it may be used. Beagle-borne board also may be used, and Intel Galileo is slightly different. Okay, that's not commonly available. And these are some of the senses. Okay, so a lot of senses are there, and the availability of the senses. I'll come across the senses, some more details in latest slides. So this is basically the type of sensors mentioned over here. There is sensors to position and position or presence or proximity to sense it. Then to sense the motion and velocity and displacement. Temperature sensors, humidity and moisture sensors, and acoustic or sound sensors, chemical gas sensors, flow sensors, force, load, torque, strain or pressure sensors, leaks and level sensors, electric magnetic sensors, acceleration or tilt sensors, machine vision and optical ambient light sensors. Okay, so these are different category of sensors. And very particularly, we have sensor modules available. These are all sensor modules which is available, readily available. Okay, so a flash memory, 7-color flash module is a small LED. Okay, can flash in 7 colors. Then a bicolor LED, then IR emission sensor, a linear Hall sensor, photo sensor, RGB, it's RGB LED, small SMD RGB LED module, then a ball switch module, then active buzzer module, button, IR, then microphone, read switch, then a tap module, heartbeat module, analog hall sensor, digital temperature sensor, and a joystick, microphone, a small microphone. It could be a condenser microphone or some other, basically some other microphone could be there. Okay, relay sensor, basically relay. Okay, that is an actuator, not a sensor, actuator. A temperature and humidity sensor and a light cup, it can sense light. Okay, analog temperature, flame, then a laser emitter, which may be used to count objects. A mini bicolor LED, RGB LED temperature sensor, again passive buzzer. Then avoid means that will detect whenever the presence is not there. Okay, Hall magnetic, light blocking, mini read sensor, rotary encoder, tilt switch, touch tracking, shock. So you can see lot of sensors. Okay, many more sensors are there. So that is how the manufacturing is, with all the use of all these sensors. Lot of parameters on the factory floor can be sensed, or during the process of the manufacturing can be sensed. So for example, it's a very simple example. There is a temperature sensor and a control circuitry along with an LED display, LCD or LED display. And so whenever this temperature is sensed, okay, so this temperature sensed automatically, that may be read by an embedded system, that may be controlled by a microcontroller, and basically the value is read as an analog value. The read analog value will be converted to the digital value, and so the digital value will be again converted into a decimal value for the display. Then the value is going to be displayed, and in that process lot of tools may be used for, it's a very small data read operation, but still it may use different types of tools. So practically whenever we are going for it, it will look like this. Okay, so we are having an Arduino Uno board. There is a temperature sensor. There is a temperature sensor, and that sensor calibration can be done by using a potentiometer, and that value will be read as an analog input, because the temperature sensor output is analog in nature, and that value will be read internally. The Uno board, it's a microcontroller board, that will be converted by using the ADC, analog to digital converter. It will be converted to corresponding digital value, but it's not a displayable value. Okay, so we cannot understand directly it. It has to be converted to the decimal value. Then it will be converted to the corresponding decimal value, and that value will be displayed on the board. And another important thing is, I already told you, so there are many Wi-Fi modules or wireless modules which may be available at a low cost as well as in a low form factor and low power factor. So that is why the IoT is easily affordable. Okay, any device can be connected to the cloud or to the common network by using this type of modules. One of the example is ESP82. Sorry, this mistake is there. 8266. It is 8266. Okay. And Wi-Fi ESP8266 and a lot of readily available tools are available. Tools are readily available. Tools can be used to manage this Wi-Fi ESP8266 module. Okay, it's a Wi-Fi module. Wireless connectivity can be very easily established to a sensor by using this module. And once that connectivity is established, the parameters from the sensor can be automatically transmitted to a network, finally to a cloud. That is the advantage. So since it is working with the basic principle of TCP/IP or internet, so it will be having a unique ID, and that unique ID is going to be configured with the Wi-Fi ESP8266 module and other parameters. Once it is set, it's something like a small computer. Okay, so similarly, we connect our computer or laptop is getting connected to a LAN. This Wi-Fi module will be connected to the Wi-Fi network. And once it is connected, the sensor associated with this particular Wi-Fi module can be very well read, and the parameters can be sent to the cloud. That is the basic idea. And it's a very good example. Okay, you can see that this, what is shown is inside of a refrigerator. Okay, so here a small embedded system is there, and that embedded system is based on ESP8266 module. What are the basic requirements for this particular module? The basic requirements are it should be powered up. So there should be some power supply. So it is battery powered. Since the 8266 Wi-Fi module is a low power module, so very well we can use batteries. For hours and hours, we can use small batteries. Okay. So that is why a battery is attached, directly a battery is attached, and the Wi-Fi module is powered up. Then what else will be there? There will be humidity and temperature sensor module. And directly the humidity and temperature sensor modules are attached to the ESP8266 module. So extra, what is there along with this 8266 module? That is only battery and the sensor. Battery and sensor. And the value will be read. The refrigerator inside values, the humidity and the temperature values will be read from inside, and that will be converted to digital value, and it will be transmitted as Wi-Fi signal. And we don't need any wired connectivity over there. Can be maybe some 10 meters it may be covered. So any server or any network, a Wi-Fi network can, which is associated to this particular Node MC or 8266 module, can directly read values from there, and that can be made available at a cloud. Okay, that is the advantage. So the size, the power consumption, everything matters. Okay, it's all going to be very low. That is why this small project is possible. And we can see another lot of things can be made around ESP8266 module. So in agriculture, it may be used like the humidity and temperature module. A soil moisture sensor may be used along with that temperature sensor, humidity sensor, mist control, and along with the sensors, it can control. Actually, this 8266 module is a very powerful module. Internally, it's having a 32-bit microcontroller, and with almost all the interfaces we need are readily available with the ESP8266 module. That is the advantage. Okay, so we can sense as well as we can control. Okay, the trip control. Trip control means there may be a solenoid valve. Okay, solenoid valve, and that solenoid valve may be controlled by a driver, a small driver circuit, and the signal to the driver circuit may be applied from this ESP8266 module. Okay, so the drip and mist. So basically, the drip and mist is going to control the temperature, humidity, as well as the soil moisture. So basically, whenever once we install the system, everything is going to be controlled. Okay, so there is no intervention of human activity over there. Without that can work. It's self-sustained. That is the advantage. And similarly, we can have a sensor network. Okay, not a single ESP module, but multiple ESP modules can be there. And one module can act as a sensor, and a lot of other modules may be installed at various locations. It can act as a wireless network. Okay, so that network will monitor an entire farm. Instead of a small area, it can monitor an entire farm. And once we got connected to the net or by Wi-Fi, if we connected to the mobile phone, a lot of applications are readily available. Applications are also there. We can write our own applications, but even if we are not writing the application, readily available applications can be used. One of the main available application is called a Blink. Okay, Blink. So Blink server, a Blink client, both are there. Okay, so once we are using the Blink, we can a lot of things can be sensed. Okay, so sensors which are attached to the ESP module can be directly read, and the parameters will be directly available. As well as it can connect different actuators or valves also. Okay, so valves, relays, whatever be it, can be directly connected to those devices automatically. Based on the sensor values, the Blink application can take decisions. We can write programs along with that, and it can take decisions, and at the output side it can control devices. So the readily available application can be one of the one of the very frequently used tool is Blink. Again, the same thing, a Blink server. Then a lot of Blink libraries are available, which may be equipped for farming or industrial application or domestic application, which can control your light, fan. So a lot of libraries are available with the Blink. Okay, so that applications can be used as per the as per the typical app scenario. Okay, so it may be an household environment or industrial environment or a farm. So depends upon that, the libraries can be used and selected and can be used. Then whenever we go for the software based tools for the development of the embedded system which is related to the IoT, we use many tools, and almost all these tools are common for other embedded system development also. Okay, the Arduino IDE that may be used for the Arduino type small computers. The AVR Studio is used by Atmel and one of the main manufacturer of microcontrollers. Raspberry Pi is also a readily available board, and the Python, Java, or Broadcom can be used. That is ARM-based programming can be used to program Raspberry Pi. Then Blink, already I told you what is Blink. And Altium, if you are little bit more concentrating on the design of the electronic circuitry, instead of having a readily available development kit, we can go for the circuit design. So in that case, we can depend Altium for that. And another tool is also help the electronic design, as well as it supports the simulation also, the Proteus. Okay. Then the fabrication, whenever we opt to the fabrication of various components of a project, we can select the CAD modeling can be fabricated by using a Fusion 360. And along with that, there may be some cloud services. Also, we have depends on some cloud services. And so some of the typical mobile applications. So this is Blink. ESP8266 Smart is used by the ESP module. That particular module is very important because it's a low cost. The price of an ESP8266 module is only around 250 rupees. That is the advantage of it. Okay, so with 250 rupees, the sensor module can be very well attached to it, and the signals can be sent wirelessly to a network. That is the advantage. Then to control the LEDs, the turn on off, the dimming control, it's all can be done by this particular LED application. Blink Home, that may be used for the domestic applications like turn on a switch, turn on or off a switch, the speed control of a fan, so all can be done. And Blink My Plant is a farming application. AgriNet is also a farming application. A lot more other applications are also available. And in an industrial environment, one of the best example what I was seeing is in the cooker factory, cooker wrangler factory, Jeep Wrangler factory. Okay, so what they have done is, so you see the number of devices which are connected. Okay, so it's a highly automated plant, and they connected 60,000 devices and robots to a central data management system in that factory. Okay, so they made it through IoT based system, and they connected to 59 assembly line robots and thousands of other devices on the shop floor. And things such as welders, sealers, to back-end monitoring systems, all connected. So one of the main examples, this is how IoT, the manufacturing is going to get benefited out of IoT. And another scenario, a bomb application. Okay, diffusing a bomb application, it needs a camera, thermal sensors, proximity sensors, ultrasound sensors, RFID, electromagnetic sensors, and other actuators, motor drives. A lot of things will be there with a robot. And recently, the advances in 3D printing. There are already a number of 3D printers in the market, from simple printers that work with plastic to complex machines that print human cells. So it's all available. And recently we would have seen a lot of concrete printers, concrete 3D printers, which can build buildings, ready-made buildings. So the copies of the buildings or customized buildings can be very well easily constructed. But sales of those printers are expected to grow substantially by in 2016 and beyond. So, but now we have printers which can print various types of materials, even large concrete buildings. Companies that make 3D printers will continue to advance in terms of their printing material like nickel alloys, carbon fiber, glass, then pharmaceuticals, biological and other materials. And ultimately may be able to print the same object. Okay, one object may be printed with multiple materials. Okay, that is the final one. So a single object can have different types of material at different portion of it. So 3D printed concrete building also. So some companies have already started building, construct building using 3D printing. And now, so whatever we have talked about basically on the technologies. Now I would like to discuss some of the projects we have already completed. So the design of a multi-color 3D printer. It's a project completed in 2014. So the importance of this 3D printer is a very common one, but it could be retrofitted a normal single color, single thread 3D printer to a three color 3D printer. Okay, 3-color 3D printer. And it could print objects in 3 materials. 3 materials, not 3 materials, 3 colors, 3 different colors. And the extruded design also changed so that it can print in 3 colors. And software is also modified, the algorithm is modified. So because it's printing with the 3 extruders, so the algorithm is modified. The mechanical modeling is done. Basically, it is a CNC based operation is being done. So the code is written in such a way that can accommodate 3 extruders, and it was one of the low cost. We retrofitted a single extruder 3D printer to a 3-color 3D printer. Basically, the 3D printing technology. So we have a 3D CAD model, and from the 3D CAD model, we have STL file. It will be sliced. Okay, so the STL file will pixelize the 3D model. Then we will be using a slicing software so that the layers can be formed out of the model. Okay, full model. And different layers. Once the layers are formed, the tool path has to be defined. So what is the way of the tool so that it can print layer by layer. The object can be completed layer by layer. One layer will be placed at the base. So above that particular layer, there may be some alteration in the base layer compared to the next one. Okay, or a new layer may be slightly different from the already printed layer, depends upon the shape. And so that is how a 3D printer operates. And the final object may be printed by the 3D printer. So the STL file, how the STL file or the pixelized Excel file is formed. It's an acronym for the stereolithography. The file format created by 3D systems, and here it does not consider the color, texture, or other common CAD attributes. So simply it will pixelize. Okay, so the object faces represented by very small triangles. And whenever we add up all the triangles, we can have the objects. You can see a ball. Okay, so a 3D ball. It is divided into so many triangles and it's miniaturized, and the size of the triangle is miniaturized so that the shape is not lost, and most widely used for the CNC applications. So it's a very commonly used for CNC applications. And whenever we go for multicolor 3D printer, basically the three colors, for example, a particular typical model is given and a base is there, and within that base in two different color, the letter 3 and the letter D are embedded. Okay, but we are not printing it together. Okay, we are not printing it together, and basically the bottommost layer will be printed. At that time, one extruder will provide the basic red color, next extruder will provide the green color, and the third extruder will provide the blue color. And in the exact positions, the printer will be, the extruder will be operational as the overall head moves. Okay, that is the basic idea. And already I told you what is a slicing software. The slicing software will slice, or it will form the layers from the basic CAD model, and slices 3D model into layers of specified height. So whenever the height is reduced, the resolution of the that particular slice will get improved, and the accuracy of the final product is very good, or the perfection of the final product is going to be very good. Okay, so it produces the G codes for CNC control. So, and it normally provides a very fast G code generation, and it reads STL and AMF additive manufacturing file, that is AMF, and object, it's an object file. And basically it combine STL file to create AMF file. Whenever the STL files for the three components of that particular model is created separately, and it will be used, the three STL files will be combined to form an AMF file. Okay, additive manufacturing file, and then the AMF file will be loaded into slicer. And once it is loaded into the slicer, it can very easily, it can be identified which extruder should be operational at what point of time. Edit print and filament settings to include two more extruder. Okay, so it will have parameters like extruder offsets, because the three extruder may be placed in a linear fashion or in a triangular fashion. So depends upon that, the offset will be set. The filament settings will be there. Filament settings means basically the molten filament will be used to produce the basic layers. Okay, the temperature settings are to be made, and the temperature at the tip of that extruder must be must be good enough to melt the material, and all other portion it should be cool. Or whenever the a molten extrude come out, automatically should set. There must be enough cool air must be there. Otherwise, if it lasts for a long time, what will happen is, in the next, whenever we place the next layer, the previous layer may not have enough mechanical strength to hold the current layer. That's going to be an issue. There could be some deformation. and retraction G code. So all done by the slicer. Uh, Being mechanical engineering faculty, you may be knowing what is G code and M code. G codes are the machine codes. Okay, machine codes which will control the movement of the machine head basically, and the M codes are used for other operations of the machine, whether the coolant should be on, the lubricant should be on, when the machine should be turned off. Okay, so that kind of operation will be done by using whenever the temperature should be turned off for the extruder. So that kind of operation, that is machine dependent operation, will be done by the machine codes, and the tool path movement operations will be controlled by the G codes. And it's a very simple notations, universally accepted programming, and normally it will be the G codes and M codes are saved as text file. So you can see the G codes and M codes. Actually, I don't get into the details of the codes, and does not need user modification. Whenever we go for once the slicer created that code, we don't have to edit the code further. Okay, and there may be T0, T1, T2 will be used to change the extruder in between. So whenever the head moves in between, depends upon the color we need, the extruder will be changed. Okay, so T0, T1, T2 is like a tool change. It's like a tool change. Printer changes from one extruder to other on seeing these identifiers. So that is what is happening and how the multicolor is getting printed. And this is a printer interface software. Okay, so here we will, after connect physically, the printer is connected. You have to set the communication port, the speed of the communication. It has to be connected. The printer has to be detected by the software. It has to get connected, and the homing of the access. So all has to be done. Then once we load the G code, based on the G code values, the tool path will be defined. And along with that, other controls also will be there. So the extruder temperature will be controlled. There may the base also will get heated up. So the temperature of the bed, okay, base or bed also will be controlled. So the provision will be there to control all those parameters. So block diagram, and the block diagram, what you can see is basically the printer must be controlled by a microcontroller or an embedded system, and the embedded system is connected to a wireless network by using a Wi-Fi node MCU or ESP8266 module. So the parameters are readily available wirelessly, and we can have a mobile application or an application which is developed in your computer system, which can be used to control. Okay, instead of having a very close control on the machine or on the embedded system itself, there may be a small screen, LCD screen, and some switches we provide on the machine or 3D printer itself to control that. But other than that, so there can have a control, wireless control for this particular machine, because all these parameters are readily made available on a mobile application also. So there are associated hardware and interface will be there. A PC is attached by using USB connectivity, and the extruder temperature is controlled by a heater, and the heater is controlled by some MOSFETs. To measure the temperature, there may be some thermistor, and the XYZ motion will be controlled by some drives and motors. So that concludes that block diagram of the 3D printer. And what we have done is we have a scrap. Okay, so a normal single extruder 3D printer was there, and it's having X, Y, Z stepper motor, so that the X, Y, and Z direction movement will be made possible with that. And the extruder will be used to extrude the molten PLA material. There is a heat bed. Over the bed only the print is going to happen. And other than that, there will be a mechanical structure which supports everything. And the first point was the normal extruder, which was very closely associated, or the pusher of the PLA thread, pusher of the PLA filament. Normally, it will be closely associated to the extruder head. Basically, whenever the head is moving, the extruder, as well as the pusher, which is a mechanism which includes a heavy stepper motor, so that it may be used to push that filament into the extruder. And so the stepper motor also will move along with the head or extruder. Whenever we include a three-color extruder, the problem is we have to have three stepper motors over the head. That is going to be very heavy. That is going to be very heavy. To avoid that, instead of having motors directly over the extruder, we have taken the pushing motors from the head to outside. Okay, so the PLA material was pushed through a Teflon tube, and this kind of extruder is known as a Borden extruder, through a Teflon tube into the extruder. And within the extruder, it will get heated up, it will melt, and it will come out of the extrusion. It will be extruded through the nozzle. It will be extruded through the nozzle. That is the basic idea. So, and so this is our extruder, and to that extruder top end, the PLA filament will be inserted, and there's a heater at the bottom side, and the heat will be used to melt the PLA material. And this is the pushing motor. You can see a small gear mechanism, and the PLA material will be passed between that gear and a small bearing, and automatically the filament will be pushed into the extruder. Okay, that is the basic pushing mechanism. And this motor, you can see the motor seems to be a little bit heavy. Since it is heavy, we cannot place one motor, maybe okay, but whenever we place all the motors to the head itself, it can give a lot of issues. Like there can be some delays in the movement. The XYZ motors may not be able to carry this much weight. So that kind of issues were there. That is why we use a Borden extruder, and it has been taken from the head to outside. And another issue we faced was when we place three extruders, the overall the entire area will get heated up. Okay, so the problem was the filament was not getting cooling enough. Whenever we place the next layer, the previously placed layer should be cooled enough. Okay, it was not getting cool enough. So we place a cooling duct, separate cooling duct. As soon as the material extruder over the position, the airflow, the cool airflow will cool down the material, and it will be solidified. Okay. And this some electronics part which can be used to control the heater. There is a power supply. There is a thermistor to measure the temperature. The heater will be controlled, and based on the value which may be given by the thermistor, a constant temperature will be maintained at the extruder as well as over the bed. And the stepper motor drivers will be used to control the stepper motors. And these three stepper motors are going to control the X, Y, and Z motion, as well as the pushing of the PLA material into the extruder. So this is the construction. Okay, here you can see. So normally the motor also will be placed along with the extruder. Here you can see three extruders, and motor also will be placed very close to the extruder. So directly the PLA material that will be rolled in three colors: green, orange, and yellow. Okay, so that will be filaments are rolled, and filament will be taken from the roll, and it may be pushed from the pushing mechanism, the pusher mechanism, and that pusher mechanism uses a stepper motor, and you can see that the pusher mechanism is taken from the head to outside that head assembly. So the weight can be reduced. Three extruders are placed, and so this is the three pushers. Okay, three pushers, and it is kept over the mechanical structure. And again, here you can see three separate extruders also can see. And this is the cooling fan mechanism. Okay, separate a duct is provided, and see, this duct is fabricated by another 3D printer. Okay, so based on the dimensions provided, so this duct is 3D printed, and a cooling fan is also placed over the duct. Okay, so a forced airflow will be there. And so that is how a 3D printer is manufactured and how it is getting connected to a Wi-Fi device. Okay, so it was instead of controlling it from the onboard embedded system, we could control it from a mobile phone by using the IoT. And another project was an automatic answer book scanner with on-screen valuation. Okay, so we know that the Kerala Technological University answer books can be, this particular project can, or the answer book scanner can automatically turn the pages. It's not single pages, it's a book. So automatically it can turn the pages, and the page will be scanned, it will be stored in an order, and it's available as a soft copy. Once the answer book is available as a soft copy, on-screen valuation will be possible. Okay, so the basic components used were a Raspberry Pi, that is for the, it's an embedded system, or a small computer board, and the motor drives. The motor drives as well as the motors are used to feed the answer books and to turn the pages, and again to take the answer book from the scan position to a stacking position. Then a vacuum cleaner is used here to whenever we go for a high power, initially you will see with the low power conditions. Okay, so we used a vacuum cleaner. So by using the vacuum cleaner only, the pages are turned. Okay, or pages are separated by the airflow, and it will be vacuum sucked. Page by page, it will be vacuum sucked, and a mechanism is used to turn the pages. And there are actuators, the laser sensors to count the number of pages scanned from a book. Whenever it reaches the maximum count, it stops. Otherwise, if one page skipped, or if one page scanned twice, so it will give error. So the scanning will be repeated. And there is a HD camera that is to take a snapshot of a page. And there will be Wi-Fi and IoT to send the scanned images to the server. Here, I'll show one video. So I hope you can see this video.
It's okay.
Yes, okay. So this is the machine. Okay, so the machine, and the pages can be, or the booklets can be stacked over here, and there is a movement for the stacking area also. Okay, it moves upward and down. Whenever some 20-25 books are stacked, okay, it will give in a space, and by going down, and so one by one it will come up, and one by one, whenever it reaches that position, so automatically that will be detected. Okay, so sensors are placed, it will be detected, and by using the vacuum cleaner, the vacuum is used to suck in the book. Okay, the book will be sucked in, and a conveyor belt will take the book to the correct position. Okay, the to position the book, again there is a perforated platform is used, and the perforated platform, whenever we place the book, automatically there is a air inflow will be there that will keep the book in place. Okay, and again the air will be blown so that the pages will be separated, and another arm will be used to turn the page. And once the page is turned, the snapshot will be taken by the camera. And the number of pages will be count using a laser sensor. Okay, And once the scanning is over, the scanned booklet will be rolled out from the position, and again it will be stacked for the storage. Okay. So again, suppose there is an error. Suppose there is an error by skipping one page or by duplicating a particular page. The number of pages will not match. So in that case, the page will be taken back and it will be rescanned. Okay. So that is the basic idea. So, and in this particular project, almost all the parts are fabricated by a 3D printer or by a laser cutter. Okay, so the manufacturing technology is used, and it is constructed. Again, the remaining metal frame is constructed, and almost all the other parts are fabricated by using the 3D printer. And at the end point, once the data is scanned or the page is scanned, it is available as a PDF file. Okay, one by one the pages will be scanned, and the pages, the data will be sent to a server. That is by using Wi-Fi module. ESP8266 module is used, and by using this Wi-Fi module and this IoT technology also will be used, and it will be sent to a server. Okay, so that is the booklet is ready for the on-screen valuation, and lot of other softwares can be incorporated to make the valuation easier. That part is not done, and what is done is the scanning of the pages or the booklet will be completed, and the completed image or PDF will be sent to a server. That will be made available on a server. That is what is done. And another project, and so this is a self-balancing two-wheeler. Okay, so this is basically based on a gyroscopic action. Okay, so and the basic prototype, initially the design and modeling is done using the Fusion 360, and some multiple models are tried. Okay, multiple models are tried. So by using gyro disk, the control of gyro disk, a lot of algorithms used, and finally, so a prototype is developed. Okay, it uses basically in the final construction, we need a gyro disk and a very high RPM gyro disk to control. And to have that much RPM, actually it's a very low cost project. And so this gyro disk was controlled by using a drone motor. Okay, since it was much cheaper, and for the prototype that is sufficient, by using a drone motor, that's a BLDC motor, and another servo control system and accelerometer. Whenever it deviates from the normal position, if there is a tilt for the two-wheeler, and that will be identified by using an accelerometer. Okay, accelerometer and a gyroscope, and that information will be automatically sent, and the tilt as well as the position of the gyroscope will be controlled based on that. That was the basic idea. And again, all these parameters were sent by the ESP module to the mobile, so that we can get all the parameters. We are not going to control it; it's a self-controlled one only. So all the parameters we could get, what is the tilt angle, how it is being compensated. So all the parameters were read, and we could made a graph out of that, and we could analyze it. Okay, that is what is done. And here another modification we have done. So I told you, to make it a low cost, a very low cost, instead of having a standard development board, the development board was designed, and it's a very good option. Those who prefer a low cost embedded system, again it is readily available as a small development board that is based on STM32F103C8T6 processor. Okay, so it's an ST microelectronics. The processor is from ST microelectronics, and the processor as well as the readily available development board costs only around 300 rupees. So it's a 32-bit processor. Again, lot of interfaces are readily available on the board, and even the CAN bus is available. That is one of the main advantage of this particular processor. CAN bus is available. You may be knowing that it's an industrial bus, and at this price, no other microcontroller offer a CAN bus. Okay, so Those who want to use an industrial bus at a low cost rate, you can prefer this microcontroller. And the entire board is developed, okay, because we need drivers for the servo motor as well as for the BLDC motor, that also incorporated, and a development board developed around this microcontroller, and it was completely developed. Development board is developed. Okay, so the PCB is fabricated and it was made available. And here also, actually, I have a video. So you can see that this is a BLDC motor. Okay, so it's a drone motor only, high RPM, it can produce high RPM, and another servo motor. And so there is a accelerometer and a development board, and there is a Wi-Fi module. Okay, so that is the basic construction. That is the basic construction. Okay, and here the constraint we faced. Actually, the entire system is only around 3 kilograms. Okay, after the fabrication, the entire system was only 3 kilograms. But we tried with the different gyro disc of different sizes, different diameters, different material, so that the weight can be different material we tried. And finally, we constructed it with acrylic material, and with 10 centimeter diameter. 10 centimeter diameter. So the complication is, whenever the entire system is some 3.5 kilograms, we are using a gyro disc with a 10 centimeter diameter. Okay, so whenever we go for the real two-wheeler, so we have to calculate the size of that gyro disc. It has to be optimized. That is the design constraint over there. Anyway, prototype is working fine, and we are further development. We are looking forward for the further development. Okay, but with a low cost budget or a low budget, whatever we can do for this self-balancing technology is this one. Okay, so that is what is completed till now. Then now the connectivity to the various sensors. Okay, connectivity to the various sensors. How we will establish connectivity to the various sensors. So the basic of IoT technology. So that is at the input side we have a lot of sensors. And output side there may be actuators. So how the connectivity will be established? Okay, to establish connectivity directly, suppose the sensor is giving the output in terms of analog or digital value, can be directly read. There is no issue with that. Okay, so any embedded system can directly read analog as well as digital value. But most of the sensors are not available as a single sensor element. It may be a module. Okay, the sensor need some power. Directly, it may not be providing a single value or a bit value, and resolution of the output has to be controlled. So yes. Anybody asking anything? Okay, I'll continue. So it has to be connected analog by using analog or digital signals, but most of the sensors are available as modules. Okay, the modules need power supply, and the module offer the output in analog or digital terms. If it is analog, the analog output voltage, or if it is a signal, the frequency of the signal matters. If it is a digital value, the number of bits used to represent the value, whether it is a parallel data out or a serial data out, it's all has to be considered. And most of the sensor modules are giving output with the standard communication protocols, and you can see some of the commonly used standard protocols. So earlier we have only UART, universe, that is a serial communication. Simply we say it's a serial communication. Okay, so the advantage of UART is it can be now the PC does not have this particular interface, but almost all the embedded systems are having. Whenever you interface to the PC, you can use USB instead of directly using a serial communication port. Converters are available. USB to UART converters are available. Those converters are available as a small dongle, and that dongle can be used. And whenever you connect embedded system to embedded system or a sensor to an embedded system, directly it can be connected, because almost all the microcontrollers are having by default UART interface is available. And the disadvantage with UART is at a time a pair can be involved in the communication, only a pair. Okay, so one-to-one communication, and the speed can be maximum of something like 9,600, and even if it goes something like 1 lakh bits per second only, not even kilobits per second. Then, but the advantage is it's a very simple interface. Whenever you go for very low speed communication, suppose only one module need to be communicated, this can be very well selected. And another communication interface is, suppose you have many devices, and all these devices are placed very closely at a close proximity. Okay, like all the devices are placed on the same circuit board. Okay, or two circuit boards may be there. We are going to interface modules from one board to the other, which is placed very closely. So in that case, we can use two protocols, that is I2C and SPI. The advantage of using I2C is multiple devices can be connected with very low interface pins, and the connectivity is controlled by the protocol only, not hardware only. And whenever, but the speed of communication is limited over there. Suppose you need megabits of speed, we can suggest or we can select SPI communication between the devices. And in this case, there is no standard protocol for the communication. Any number of bits can be transmitted. So a bulk of data transfer is very easy, and it offers high-speed communication. So that kind of advantages are there. And CAN bus is another totally different interface. The CAN bus is used is an industrial communication, because in the industrial environment or inside an automobile, the interferences by the external signals are going to be very severe. There can be data loss due to some surges, some interferences, external interference, and a lot of things are there. So the signals are to be protected. The real data is to be protected from external interferences. There we can use CAN. CAN offers a very rugged or reliable data transmission, and multiple devices can be simultaneously connected to the CAN bus. And again, the CAN offers a real-time communication. Here, there is only one disadvantage is there. The maximum data transfer is limited to 1 Mbps. And another option is Ethernet. You know what is Ethernet? So everybody is getting connected to the internet by using a LAN or a Wi-Fi. Okay, there comes the wireless Ethernet or Ethernet. Okay, so we are all getting connected to the common network by using Ethernet, wireless or wired, whatever. And USB is multiple devices can be connected to a hub. USB hub is a very commonly used protocol. And embedded system to a personal computer interface is possible. Embedded system to embedded system interface is possible. PC to PC interface is possible. And again, it's high speed. That is advantage of using USB. Wi-Fi is main advantages. It belongs to the Wi-Fi, and again, based on the TCP/IP or Ethernet, it operates. and offers a very high speed data transmission. And Bluetooth, we have low power Bluetooth is also available. Bluetooth itself is low power, and it's a low profile interface. And Bluetooth BLE is the low power Bluetooth. Okay, that is also available. Zigbee is also low power, but it needs a coordinator, something like a server client management, like that. Okay, and EtherCAT is a real-time version of the Ethernet. One of the main disadvantages of Ethernet is it's not real-time. The data which you send over the internet is not guaranteed. Okay, it does not offer any guaranteed delivery. It could take more time. There can be delays, or even it may not be delivered. Okay, that can happen. Okay, but in the case of Ethernet, it's a real-time version of Ethernet. Okay, and it's an industrial connection also. So we have different protocols which can be used to connect, to interconnect the sensors, because sensors are available with the standard protocols. Normally, the sensors are available with the standard protocol, and many sensors are available with the UART interface. And lot more sensors are available with I2C or SPI type interface. And especially the sensors which is used in the vehicle are available with the CAN bus, okay, CAN interface. And Ethernet, we know almost all your laptops or the embedded systems, most of many microcontrollers are readily available Ethernet interface. USB is also available with many microcontrollers. Wi-Fi, directly Wi-Fi is not available with the microcontrollers, but we already come across with ESP8266 and WROM type small profile Wi-Fi modules. And these modules can be attached to the embedded system by using UART or by using I2C or SPI. And Bluetooth, you know what is Bluetooth, and that is also extensively used. Bluetooth is also, Zigbee is also, especially in experimental purpose, we use Zigbee. EtherCAT industrial instead of using CAN bus, because EtherCAT offers a very good bandwidth. It's as good as Ethernet, okay, and it offers real-time operation also. So these are the some of the interfaces, okay, which can be used to connect the sensors or actuators to the IoT. And we will go through some of the interfaces and some tools which is generally we use for the development of interfaces in electronics, okay, in the design of embedded systems. We will go through UART, I2C, and SPI. We will see how we communicate using two embedded systems are going to communicate using UART and or I2C or SPI. And so we will go for some simulation so that you can get acquainted with some simulation software. So we will start with the UART interface. Okay, UART interface. So this Lab Central Electronics Proteus, the same embedded system or the electronic design software, as well as some of the simulations also can be done so that we can test our circuit, we can test our program. I hope you can see the circuit.
Yes, sir, it is visible, sir.
Yeah, okay. Here you have two microcontrollers. It's an Atmel based microcontroller. Okay, 89C 51. Okay, that is a microcontroller. These two microcontrollers are connected serially. That is normally a serial connection means it's the UART connection. Okay, UART connection in embedded systems. Okay, so it's connected serially from these are the connection lines. Okay, so we skip all other unwanted connections over here. Okay, so basically we have the default power supply, default oscillator, everything we use default. Okay, what we connect is this is the interface. That means the transmit and receive lines are connected over here, and to test whether our interface is working properly, So we have switches. At the input side, we have switches. That is indicated as 108 switches are there because 1 byte we are going to transmit. 1 byte, 8-bit information we are going to transmit. And so the same data will be transmitted over the line, and it will be received at the receiver end. Okay, at the receiver end. Okay, so the same data is going to be received over here. And once the data is received, that will be indicated over these indicators. Okay, so the transmitter, the input switches, and the receiver and the output indicators. And so this particular simulation software, those who are acquainted with the software can very well embed a program into that. And those who are not that much acquainted with the electronic design, you can see that how the simulation software is going to work. So I'm going to edit the properties of the software. And whenever we write a program, it's a software controlled operation. Okay, software controlled operation. For that, basically, we should have a program. Okay, so we should have a program, and that program should will explain how this is going to happen. Okay, so here we are. I have the transmit program. This is the transmitter program. So this is the transmitter program, and here basically I am not going to explain everything. Okay, basically what we are doing is we initialize the communication and we set the data transfer speed. Some standard speed we have to set. We call it in serial communication. We call it baud rate. That is the bits per second. Okay, so the bits per second is configured as 9600. It's a very commonly used, widely used baud rate in serial communication. Okay, so that we set, and remaining part is the code to send the data. Here we are controlling the speed, and once that data is sent, and that will be received at the other side. Okay, basically through serial communication channel, it will be sent by bit by bit. That is a serial communication. Okay, so bit by bit the data will be sent. And so once the program is written in the corresponding software, the program will generate a code. Okay, so here we have our simulation model, and we have two embedded systems or two microcontrollers. One is a transmitter microcontroller, and the other one is a receiver microcontroller. So transmitter may have some particular sequence of operation to transmit the data, and at the receiver end there is a sequence of operations to receive the data. We have written the program corresponding to the transmitter and the receiver programs, and that codes are going to generate an output file, and output file format is hexadecimal file. Okay, hexadecimal file. Simply we say the hex file, or the file format is going to be .hex. Okay, that is file format, and this is the file which generated, and from the destination folder, I selected that program, and that particular program is supposed to be embedded into the microcontroller. That is the meaning of it. Whenever I select the program file over here, that is supposed to be embedded into the microcontroller. Similarly, at the receiver end also, I have the receiver program. You can see that corresponding to the receiver program, by compiling, the code will be generated, and the corresponding code is going to be embedded into the microcontroller. Now the microcontrollers are ready to transmit as well as to receive. And now I am executing this one. Okay, so whenever it's getting executed, what will happen is, you can see this this 100, this particular pattern is transmitted over here. Okay, now I am changing 1 bit. You can change the corresponding, you can see the corresponding change over the other end. So the real data is going to be transmitted to the other end. Okay, so that is how a UART communication operates. Instead of one microcontroller, this is to indicate I need to have a microcontroller. Okay, two microcontrollers I need to have. Instead of one microcontroller, one could be an actuator or a sensor which is having a direct UART interface. Okay, so sensor will give the value, a digital value, a serial and in serial fashion, and that will be transmitted to the microcontroller. Microcontroller can read it. Microcontroller can read it, and automatically the value can be saved inside the microcontroller or into the microcontroller, and appropriate actions can be taken. Okay, this is how it operates. Okay, so and similarly, so this is a simple one. Okay, so we have only two microcontrollers, and I already told you UART is a very simple interface. UART is a very simple interface. Similarly, we have and little bit complicated sensors will have, or the sensors which need more faster bit transfer, more bandwidth. Okay, that will not prefer UART. Okay, that will prefer I2C. If more number of sensors are there, it will go for I2C interface. Okay, and whenever we go for I2C interface, here instead of having two microcontrollers, I'm using two separate Arduino boards, Arduino Uno boards. Okay, and these two Uno boards are connected by using I2C interface. Okay, these two lines are used for the interconnection between the two Arduino development boards, small computers. These two are small computers. Okay, and to these small computers, a temperature sensor is attached. Here you can see that temperature sensor is attached, but this temperature sensor is does not give the output in terms of UART. It's giving analog output only, and that analog output will be read by the Arduino board by using its ADC pin, analog to digital converter pin, and the value will be available as a digital value inside. Okay, and that value is going to be transmitted by using the I2C interface to the other microcontroller or to the other Arduino board. And in both boards, I placed two LCDs so that the red value can be displayed on the LCDs. Okay, now the hardware interface is through, everything is connected, the temperature sensor is connected, two embedded boards are there. The embedded boards are interconnected by using the I2C communication to indicate the value from the temperature sensor on the first embedded system. LCD is there, and similarly after transmission, the receiver Arduino board will receive the data, and that also going to display the value over there. Okay, so now I am going to execute it. You can see that the temperature read from the temperature sensor is going to be 35.23. That the first microcontroller indicates 35.23, and okay, a little bit I will enlarge it. Okay. Yeah. On the temperature sensor, the simulation model is giving 35 degrees centigrade, 35 degrees centigrade. And on the first microcontroller, it is not 35, it's 35.23. And the second microcontroller, it's exactly 35. Why is happening? Okay, you can think about it. I will give the basic idea. So whenever the ADC is converting, it could be 8-bit ADC, 12-bit ADC. So directly the ADC value is going to be converted, and the first microcontroller is taking the entire value, and that value is going to be displayed. Okay, and whenever transmitted, so the transmitter is using only 8-bit. Okay, so it's 8-bit or a byte of information only will be transmitted. So it will truncate some portion of the input value. Okay, if the original value was 12-bit, some portion of that particular original value is truncated. Anyway, it transmits only 8-bit, and the truncated value is going to be displayed over the receiver microcontroller. So that is why there is a small difference, and difference will be only there in the decimal value. Okay, so the truncated value is restricted over there only. So the basic that integer value which is provided from the temperature sensor is it's not going to change. Okay, there won't be any change. But and in the second microcontroller, after, even if I am changing, I can change the I can increase or decrease the temperature value over here by pressing the plus there is a up arrow and a down arrow are there. Whenever I press the up arrow, the value will change 37. But the receiver microcontroller, it will take a small delay. That is due to, because we are using a simulation model, And due to that difference, okay, so difference in the simulation only, this difference is giving. Otherwise, there can be some propagation delay, but that may not be noticeable in the real time or in the practical scenario. Okay, I can decrease as well. So value is getting decreased. Okay, so this is how an I2C interface works. Similarly, instead of having one microcontroller on the other side, we can have a real sensor. Okay, that sensor may be giving values in terms of I2C interface. Okay, so that value will be read and it will be displayed or whatever. So once we are having the value, it's a control system. Okay, so the system can take decisions based on that. And one more interface, already time is over, only 1 minute I'll take. Anyway, I plan to complete that portion also, so I'll show that one also and we'll finish. And that is by using SPI. So main difference between I2C and SPI is multiple devices can be connected in the case of I2C. In the case of SPI, it can go speeds like hundreds of megabits per second. Okay, so that is advantage. Whenever you have a large amount of data to transfer, don't go for I2C. And suppose you have some 50 devices, 50 sensors you are using, you cannot use SPI effectively. Okay, so in that case, you have to use I2C. Okay, so suppose you need a bulk of data has to be transmitted from one device to another device, then prefer SPI. So all the interfaces, all these communication interfaces are having its own relevance. Okay, in terms of speed, bandwidth, then number of devices can be connected, the type of interface, whether it is wired or wireless, so it will vary. So we have to choose. And here also, a temperature sensor is connected to one microcontroller, and here the interface is not by I2C, it's by SPI. So that you can observe SPI. Very particularly, the SPI interface is by using some special pins. So that is how we identify whether it is SPI or I2C just by seeing the circuit diagram. Okay, so here also I'll execute it. Yeah, now, okay, so you can see that the temperature sensor is giving values, and that value is read on one embedded system. It's transmitted to another embedded system by using SPI over here, and it's displayed on the other system. Okay, so this is how we come across with multiple tools. Mainly, almost all the tools I explained belongs to electronics, because I concentrated on design of electronics associated with IoT. Okay, so we can stop it here. And okay, we have gone through the interfaces by using UART, I2C, and SPI. I think almost it's time's over, and whatever I planned is completed. And those who want to ask some clarifications, some doubts, whatever be the questions, you're free to ask.
Thank you, sir. Thank you for the wonderful presentation. Now it is up to the audience. Any questions or clarifications? Any questions from the audience?
Any questions? Any doubts? Was I too electronics, concentrated too much on electronics, so that you could take? Okay, sir. Okay, then thank you very much for giving an opportunity to present whatever I know regarding these basic technologies. So it's a great opportunity actually. So thank you, Shanmugh sir.
Thank you, sir.
And thank you the entire team. Okay. And
Let me invite Mr. Arun Kher for the vote of thanks.
okay.
Thank you, sir. Thank you, Dr. Ajit, for a value session. So I am very sure that all the participants in the sessions gained a knowledge in IoT tools for automation and manufacturing. And on the behalf of Department of Mechanical Engineering and all the participants, I extend our sincere gratitude. Thank you, sir.
Okay. Thank you very much.
Thank you, sir. Thank you for the wonderful sessions.